Hello everybody, I just want to make a quick video on the last topic that I'll cover in the section on Gibbs free energy and entropy. We will use this type of information for the remainder of the course in many problems, but this is the introduction to it, if you will, and I'm going to wrap it up today with a quick video on how to calculate for a given reaction, such as the one I have written here with magnesium, oxygen, giving you a solid state magnesium oxide, how to calculate the Gibbs, the change in Gibbs free energy standard. It's per mole for a given reaction. The RxN here is sort of superfluous, just meaning it's for a chemical reaction and not like maybe a phase transition or something else. And the little zero or not symbol, whatever it's called, is just telling you it's done under standard conditions, because we work in a standard state typically to make tables and so forth as a reference point. Of course, you can have experiments that deviate from that, but that's usually what we characterize in terms of tables like the one in the back of your book. And if you don't have the book, which is fine, I always put those type of tables online, and honestly, you can Google those tables in seconds. So I'll have something accessible that's called thermodynamic tables or similar online for you, so you don't have to worry about that. So this is, you want to know the free energy associated with a reaction. This could tell you, for example, under the conditions you're working in, which is in standard conditions in this particular case, if you're spontaneous or not, if it's going to go or not. Also note, when we have, we're telling ourselves we're standard conditions by that little symbol here. Standard conditions are independent of temperature, but they're tabulated at a temperature, and they do vary with temperature. So typical, most tables are at 25 degrees Celsius or 298 Kelvin. You could have standard state values. Maybe you're studying the human body with biochemical reactions that are particular to it, so you could tabulate them, all these molecules of interest, their thermodynamic properties at, say, 37 degrees Celsius, whatever that is in Kelvin, and make a table of that. I would say the values would probably be similar to like 3 sig figs or more, but if you needed something highly accurate, they could certainly be tabulated there as well. Or if you're doing industrial processes at very high temperature, you could tabulate standard values for them as well. So we'll work with the table at 25 degrees Celsius or 298. There's two ways of doing this calculation, and I'm going to tell you the way that's easier to do it, because the table I will give you, and anybody reasonable would give you that table because it's tabulated data. Way one, which I consider to be actually harder to do, is use the relationship delta G is equal to delta H minus T delta S, and just put it in the form of for a reaction if you're looking for standard conditions under standard conditions, and then go back and you would calculate delta H a reaction the same way you did last semester, using the standard enthalpies of formation. You sum the products minus reactants as you did before. The same kind of form as what I have written here, except these would be H's for enthalpy of formation. Standard, and then you do what we did in the last lecture, as you would have temperature multiplied by the delta S of a standard molar entropy of a reaction. That's fine, but like you have to do really 1-2 calculations to get something. You can do it in one step, and this is what I'm going to show you right now, how to do it. You have the components to do this, and you can verify the results that I'll do with the more succinct method, with the longer method, to make sure that they both work. And you can do both, but I'm going to do it the easier way, which is that delta G of a reaction under standard conditions per mole is equal to the sum of the coefficients of the products from a balanced equation. Like here would be a 2, products would be, a 2 here, and then the delta G standard, this is the change in Gibbs free energy of formation under standard conditions per mole. Okay, so what delta G of formation is, it's analogous to delta H of formation standard. This would be the Gibbs free energy for 1 mole of reaction unit to go from the most stable elemental forms of something, which is exactly what we have here. This would be showing us this is the most stable form of magnesium, is magnesium solid at room temperature. The most stable form of oxygen at room temperature standard conditions is O2. Forming the product of interest. So this is actually what we're showing here is a formation type of reaction for an element. And so, but you can use this for any type of reaction. The thing with this is nice, and then we subtract that off for the reactants, which in this case, magnesium and oxygen, and we need to have the correct coefficient. So you go to the table, and these are all tabulated by, they'll have a magnesium column and an oxygen column and so forth. Magnesium oxide's probably in the magnesium column. And always look at the phase. The phase makes a difference. So they could have, for example, you might have CO2 in the gas phase, but CO2 dissolves in water well, so they might have an aqueous version of it and so forth. And so you want to pay attention to that. HCl, you work with in the lab, it will have a gas phase. Definitely it goes to a vapor readily, but it will definitely have the aqueous phase. That's what you make solutions over. The thermochemistry of that's important. So for water, they'll have ice, a solid, liquid, and gas. So be careful of the phase. That varies a lot. So you go to the table and you start to look up delta G formation. Now these are energies. They're not the same as the entropies. Always have a positive value. With these, we define delta G of formation to be 0 for the most stable elemental forms at that under standard conditions at that temperature. So it turns out when we do this calculation here, I'm going to just write it out how it looked. Delta G for this reaction here of interest, this reaction we're forming magnesium and oxygen, forming magnesium oxide, would be products. So the products would be equal to 2 times delta G. I always forget where to put the 0 on the F because different books do it different ways. Formation, I'll just write here magnesium oxide solid. So we look up that value minus, I always put this here, parentheses, 2 times delta G formation for the magnesium solid. This is magnesium oxide, this is magnesium solid, plus, there's just a 1, I won't write it, delta G naught formation of what? So we have, this would be O2 gas phase. Now the great thing is for this particular problem, we looked this up in the table, we have 2, and then we have, this ends up being, and I don't have to commit to memory, negative 569.0. It's in kilojoules per mole scale, and most of the energies on there are in kilojoules. If you do these calculations here, these are usually joule per Kelvin per mole on the table. So this is in kilojoules per mole, just like the enthalpy would be. And then the other two terms, this magnesium solid is the most stable form of magnesium at room condition standard, room temperature standard conditions, and O2 gas, similarly, is the most stable form. So those are both zeros. So this is a minus 0. So this ends up being minus 1138 kilojoules per mole, meaning that's a negative, that it's spontaneous under room conditions. If you want an exercise to practice, go back and look up the delta H of formations in the table and calculate delta H naught of reaction, the same way you did last semester. And then calculate delta S naught of reaction the same way we did in the last video, the video before that, where we did some calculations. We used the standard molar entropies for the elements, and you'll see, you'll come out with a very similar answer. Again, these are experimental values, so if you come out with negative 1136 or negative 1137 or something like that, I mean, that's just because of rounding and it's experimental data and so forth. Don't freak out, say it's different. Might be 1 or 2% different because these are tabulated values. But, show that you should come out with very similar values within a couple percent. So, at any rate, this wraps up this video. And we'll move on to a new chapter in the next one. And so have a good day, and maybe I'll make another video.